In this lecture, we're going to start looking at how organic compounds are named, delving into organic nomenclature. When studying organic chemistry, it's kind of convenient sometimes to think of organic molecules as really just a chain or collection of carbons that are decorated with other things. A hydrocarbon is really the simplest case. A hydrocarbon is a molecule made up of only hydrogen and carbon. Heteroatoms are other atoms, things like nitrogens and oxygens and halogens that can be attached to any of those carbons. Now, the simplest of all organic molecules are alkanes. Alkanes are hydrocarbons, so they have no heteroatoms, but they also have no pi bonds. And remember, that simply means they have no double or triple bonds. So here I've got the smallest three alkanes. A one-carbon alkane, methane, which you're familiar with as the main component in natural gas. We have a two-carbon alkane, ethane, and then a three-carbon alkane, propane, which you're also probably familiar with from backyard barbecue grills and such. Now, when we start introducing other atoms, heteroatoms, and other types of bonds like double bonds and triple bonds, we introduce functional groups. A functional group is a collection of atoms and bonds with a characteristic chemical reactivity. So here I've got a couple of examples. I've got a two-carbon chain with an OH attached to it. That's a functional group. It's actually an alcohol. We'll learn more about those later. In our other example, we have a carbon that is double bonded to an oxygen and then a single bond to a chlorine. This is called an acyl halide, just another functional group. Now, they're called functional groups because they behave the same no matter what molecule they're attached to. If you see an OH bonded to a carbon chain, it doesn't really matter what the rest of that molecule looks like. It's going to behave roughly the same. Now, before we can really go any further in looking at how organic compounds are named, we do have to take another look at drawing molecules. We're going to be looking at much larger and more complex molecules, and that really necessitates less detailed and faster ways of drawing things. So I'm going to show you two new types of structures. The first, condensed structures. A condensed structure is an abbreviated structure that groups together identical atoms and omits most of the drawn bonds. When looking at condensed structures, it's important to recognize the difference between multivalent atoms and monovalent atoms. Multivalent atoms are those that typically make more than one bond, atoms like carbon and nitrogen and oxygen, whereas monovalent atoms are those that typically make one bond, usually hydrogens, but a lot of halogens. When you look at a condensed structure, what typically is happening is we take each multivalent atom and we see what monovalent atoms are attached. And then we indicate how many of those atoms there are with a subscripted number. So if you look at propane, the leftmost carbon, that's a multivalent atom, and it's bonded to three hydrogens, which are monovalent. Yes, it's also bonded to another carbon, but that's another multivalent atom, so we're going to ignore that for now. So that leftmost carbon has three hydrogens attached, three monovalent atoms. So we group all those together, and we simply draw it out as CH3. The next multivalent atom in the molecule is that middle carbon, which has two monovalent atoms attached, two hydrogens. So we abbreviate that as CH2. And then the third carbon is kind of the same as the first, right? It's a carbon with three hydrogens. Those are monovalent, so we abbreviate it as CH3. Now, the actual bonds connecting the multivalent atoms can also be omitted. In fact, that's probably more common. I like to draw them out sometimes, but it's perfectly okay to just draw out CH3, CH2, CH3 in a fully condensed structure. By far the fastest way to draw any organic molecule is to use a skeletal structure. This is a highly abbreviated structure in which all the carbons and hydrogens are actually implied and not drawn out explicitly. This is how it works. You simply draw a line that represents each covalent bond between carbons. The end of each line and the intersection of any lines represents a carbon. So if we draw out propane, we would simply draw out two lines connecting. Now, there are hydrogens implied attached to each of those carbons, and we imply enough hydrogens to match the charge drawn for that particular atom. So there are no charges in propane, so it's kind of simple. If you look at the leftmost carbon, that's the end of the line, right? That represents a carbon. And as drawn, there's only one bond drawn to it, right? That carbon-carbon bond. And remember, for charge purposes, When you're counting electrons, you count half of every bond and then any lone pairs that are there. Well, there are no lone pairs, but there is one bond. So we take one electron, and that means that this carbon, as drawn, has only one electron on it. But carbon is in the fourth column in the periodic table, so it wants 4 electrons to be neutral. So we imply that there must be 3 hydrogen atoms attached, each contributing 1 electron, therefore giving it 4 total, and therefore being neutral. So that end of the line on the left is actually a CH3. The carbon on the right is the same, right? If you look at the far right, that end of the line is also a CH3. It has 1 bond drawn, so we imply 3 hydrogens to bring it up to a charge of 0. The middle carbon, the carbon represented by the intersection of those 2 lines, well, as drawn, it has 2 bonds attached to it. And so for charge purposes, that means it has 2 electrons, but it's neutral, right? There's no charge on it. Carbon being in the fourth column wants 4 electrons to be neutral, so we imply that there must be 2 more hydrogens attached to it to bring it up to the right electron count to be neutral. So that's a CH2, and that's exactly what we have in propane, right? CH3 bonded to CH2, bonded to CH3. Skeletal structures are very powerful because they're very fast, but they're also very dangerous. Because so much is implied, it's easy to forget that all those atoms are really there. And it's very easy to kind of introduce extra hydrogens or obliterate hydrogens inadvertently when you're dealing with these structures. So you do have to be really careful with them. Now, organic molecules deal mostly with covalent bonds, and covalently bonded species have a lot of structural diversity. Isomers are molecules that have the same formula but different structures. Constitutional isomers are isomers that differ in exactly how the atoms are interconnected. So I've got a couple of examples here. We've got 2 compounds. Both have the same formula, C4H10. But the atoms in both compounds are actually connected differently. If you look at the first molecule, butane, you can see that it has a CH3 connected to a CH2, and then another CH2, and then a CH3. The second molecule, isobutane, we have a CH3 that then goes on to a CH and then kind of goes in 2 different directions to separate CH3s. Butane is an example of a straight chain alkane. If you start on one end of the chain of carbons and you progress to the next carbon down the chain, it can only go to 1 carbon at a time. So if you start on the far left, it goes to the next carbon, and the next carbon, and then to the last carbon. Isobutane is an example of a branched alkane. If you start on any end of the chain, at some point you're going to get to a carbon that can then go on to 2 different carbons rather than just to 1. So if you see in the center of isobutane, there's that carbon that can actually go on to 2 different carbons. And it turns out that the more atoms you have, the greater diversity of isomerism you have. When you have 10 carbons, a 10-carbon alkane has the formula C10H22. And it turns out that there are 75 different isomers with that formula. And coming up with a unique name for each one of those isomers is a really daunting task, unless you have some kind of a process, a procedure to create names. The procedural way of generating names for organic molecules is referred to as systematic or IUPAC nomenclature. IUPAC is just an acronym. It stands for the International Union on Pure and Applied Chemistry. Now, systematic nomenclature is based on the ideas of parent chains and substituents. A parent chain is really just the main contiguous chain of carbon atoms, and for an alkane, that's simply the longest carbon chain in the molecule. A substituent is an atom or group of atoms that have replaced a hydrogen on the parent chain. So if you look at this molecule, the longest carbon chain is that 7-carbon chain kind of going left to right. That's the parent chain. Then we have these 2 other chunks in red that are attached to it. Those are substituents. If those were hydrogens, then we would just have that 7-carbon chain. But those substituents introduce branching to the molecule in this case. But they're not hydrogens. They are groups that have replaced hydrogens. In this case, CH3 groups, if you think about it. And those CH3 groups are called alkyl substituents. An alkyl substituent is just a group that is comprised of an alkane minus 1 hydrogen. Alkyl substituents are named after the alkane that they kind of came from, the alkane that you would have removed a hydrogen from. So CH4 is methane. You remove a hydrogen to make CH3, it becomes a methyl group or methyl substituent. Ethane, a 2-carbon alkane, CH3, CH3, remove one of the hydrogens, you get CH3, CH2, and ethane is now an ethyl group or ethyl substituent. So the first kinds of compounds we're going to learn how to name are alkanes. In fact, alkane nomenclature is really the foundation of all nomenclature. If you can learn how to name alkanes, everything is kind of just a derivative of that. And it's a procedure. There are going to be multiple steps to this, and you have to do them in the right order. The first part of naming any compound, but certainly naming alkanes, is to determine the parent chain. And remember, with alkanes, the parent chain is simply the longest carbon chain in the molecule. So if you look at this example, I have a 4-carbon chain. We name that parent chain, that 4-carbon chain, based on the number of carbons that are there. 4 carbons in this case. So here, I'm showing you the names for the 10 smallest alkanes. We have a 1-carbon alkane, which is methane, then 2 carbons is ethane, 3 carbons propane, 4 carbons is butane. And then we have pentane for 5 carbons, hexane for 6, heptane for 7, octane for 8, nonane for 9, and decane for 10. And yeah, just commit these to memory, right? This is the basis of all nomenclature, so these 10 names you've just got to learn, but a lot of them are pretty simple. So going back to our example, we have a 4-carbon chain, so this is going to be a butane. And because it has no substituents, it's just a straight chain molecule. That's it, we're done. It's butane. Most of the rules we're going to look at now deal with what happens when you have substituents attached to the parent chain. If you only have one substituent, you always start from the first rule, right? You got to go back and figure out what is the parent chain. So if you look at this example, the longest carbon chain is again 4 carbons. So it's butane. This butane has a substituent attached to it, right? It has a branch point. What we're going to do now is we're going to number the carbons of the parent chain. And we do this by starting on the end of the chain that is closer to that substituent. So in this case, if we start on the left carbon, we would get to that substituent. It's a methyl substituent on the 2nd carbon. If we started on the right side, it would actually be on the 3rd carbon. Since that's a higher number, we don't do that. We start on the left in this case. So we can then number all 4 carbons of the parent chain, in this case, left to right. So now we can see that that substituent, that methyl group, is attached to the 2-carbon of the parent chain. That 2 is called a locant. It's essentially the position of that substituent on the parent chain. And we simply place that locant in front of the substituent name, separated by a dash. So in this case, it would be 2-methyl. And then we attach that to the parent name of butane. So 2-methyl butane. And this is how pretty much all substituents are introduced to a name. You place the substituent in front of the parent name, and then you put the locant value in front of the substituent name. Remember to always separate a locant from any letter part of a name with a dash. Most of the remaining rules for generating systematic names for molecules deal with what happens when you have more than one substituent. So if you have multiple substituents, you're going to do the exact same thing. You're going to figure out what the parent chain is. So if you look at this example, you can see that the longest carbon chain is the 8-carbon chain going across horizontally. We then number the parent chain. In this case, because we have more than one substituent, we simply start the numbering from the end of the chain that is closer to any substituent. Doesn't matter which one it is, just whatever one is lower. So in this case, numbering from left to right, we would get to a substituent, a methyl substituent on 3. If we started on the right, we would actually get to a substituent, an ethyl substituent on 4. And since 4 is not lower, we start from the left side, right? That gets us methyl on 3. So in this case, we number the parent chain left to right. We can see that we have a methyl group on the 3rd carbon and an ethyl group on the 5th carbon. Because we have multiple substituents, we put all of those substituent names in front of the parent name, which is octane in this case for 8 carbons, and we list them in alphabetical order. So ethyl first and then methyl. Each substituent preceded by its locant and a dash. So in this case, we have 5-ethyl, 3-methyl, octane. And you'll notice there is an extra dash in there. Remember, you always separate locants from letters with a dash, and that's why we have that extra dash between the ethyl and the 3. Now, multiple instances of the same substituent are treated a little differently. If you've got multiples of the same group, so if you look at this example, Again, go back, find the parent chain, which in this case is the pentane going horizontally. And yeah, we would still number it the same way. We would start on the end that is closer to any substituent, which in this case would be the left, so we would number left to right. And when you see that, what we have here is a pentane with two substituents, two methyl substituents. Those are the same kind of group, right? Two methyls. So rather than saying 2-methyl, 3-methyl pentane, we group together the methyls with a little prefix that tells us how many there are. In this case, since there are two, we use the prefix di. If there were three, we would use tri, tetra for 4. And then after tetra, it follows the same kind of naming convention that the alkanes did. Penta for 5, hexa for 6, etc. So in this case, what we have is 2,3-dimethylpentane. We put both locant values in front of the dimethyl, and we put those in increasing numerical order, 2, 3, and the locants themselves are separated by a comma. So 2,3-dimethylpentane. Remember that each substituent does get a locant, even if it's the same value. If you had two methyl groups sticking off of the same carbon, you would have to list the same locant twice, like 2, 2 or 3, 3. The next couple of rules deal with what happens when you have ties in the numbering of the parent chain. So what happens if you have two substituents that are equidistant from either side of the parent chain? Look at this example. We can see that the parent chain is going to be this 9-carbon chain going horizontally, and we have 3 substituents. Starting from the left, we would get to a methyl substituent on the 3rd carbon. Starting from the right, we would also get to a methyl substituent on the 3rd carbon. So it's a tie. So in that instance, what we do is we ignore the first substituent that we encounter starting from each end, and we simply go to the next substituent that we would encounter from each end. So starting from the left, we would ignore the first methyl group, and then the next substituent we would encounter would be that ethyl group on the 4th carbon. Starting from the right, if we ignore the first substituent, the next substituent we would encounter again is that ethyl group, and the ethyl group would be on the 6th carbon, and that's a higher value. So we're going to go and start from the left to give that group the lower value. So it's pretty straightforward. If you get a tie from starting on either end, ignore the first substituents and just look at the next substituent starting from either end. So in this case, there's really nothing else new. We have a nonane for 9 carbons. We have 2 methyl groups, one on 3 and 7, so that's going to be 3,7-dimethyl. And then we have an ethyl group on 4. And so we have to alphabetize that. 4-ethyl, 3,7-dimethyl, nonane. And if you look at that, you might at first think I made a mistake, right? Because ethyl does not come before dimethyl alphabetically. But for naming purposes, it does. The counter prefixes are ignored when alphabetizing. And it actually makes a lot of sense. There's an easy way to remember this, in fact. Just ask yourself, is there such a thing as an ethyl substituent? Yeah, it's a CH3, CH2 group. That's an ethyl substituent. Is there such a thing as a dimethyl substituent? No, right? There is no such thing as a dimethyl group. A methyl group, yes, but not a dimethyl group. Dimethyl simply is telling you that there are 2 instances of methyl groups, and methyl is an actual group. So that's how this works. We're alphabetizing the group names, ethyl and methyl, and that's why ethyl comes before dimethyl. Now, occasionally you'll encounter situations where there's what I call an absolute tie. So let's look at this example. Again, find the parent chain. In this case, it's going to be the 7-carbon chain going horizontally. And for numbering that parent chain, if we start on the left, we're going to get to a substituent on the 3rd carbon. And if we start on the right, we're going to get to a substituent again on the 3rd carbon. So it's a tie. And the previous rule tells us that what we should do is ignore those groups and go to the next group, starting from each end. And we can do that. Starting from the left, if we go and ignore the methyl group, we would get to the ethyl group on 5. And if we start on the right and we ignore the ethyl group, we would get to the methyl group, but again on 5. There's only 2 substituents and they're equidistant from the ends, so there's really no other way to break the tie. So what we do here is we simply rely on the alphabet. Whichever group comes first alphabetically gets the lower locant value. So in this case, we're comparing a methyl group and an ethyl group. Ethyl comes first alphabetically, so we start on the side that is closer to the ethyl group. So in this case, we're actually numbering right to left. After that, it's pretty straightforward. We have 3-ethyl, 5-methyl, heptane. Don't forget to alphabetize those 2 substituents. Occasionally, you're going to run into molecules that actually have more than one unique parent chain. And by that I mean you can find multiple instances of the same greatest length carbon chain. Look at this example. There are actually two 7-carbon chains in this molecule, and they're distinct from one another. The first one is the one that kind of just goes straight across horizontally. But there is a second 7-carbon chain. It kind of hooks downward. If you start on the right, move your way to the left, it kind of goes down. And you can tell those are actually different. It's actually easy to tell. If you look at the 7-carbon chain that goes straight across horizontally, you can see that it actually has two substituents attached to it, right? A methyl and an ethyl substituent. If you look at that other 7-carbon chain, the one that kind of loops downward, it actually only has one substituent attached to it. And that substituent is a branched substituent. It's not a simple alkyl group. And branched substituents are actually really kind of a pain to name. So we tend to avoid those whenever we can. So the rule here is pretty straightforward. If you have two potential parent chains of equal length, in this case, the longest chain is 7 carbons, but there are two ways to do it, you choose the one that actually has more substituents, because that actually winds up generally giving you a simpler name. Once you're past that, this example is very straightforward. We number that 7-carbon chain from the end that is closer to a substituent, which in this case is going to be numbering from left to right. And then we identify the two substituents, in this case methyl and ethyl. We put it together, so we wind up having 3-ethyl, 2-methyl heptane. Very related to alkanes are cycloalkanes. Cycloalkanes are just alkanes that have looped around to form a ring. Now with cycloalkanes, the parent chain is going to be either the ring itself or some other carbon chain, whichever one is longer. So I've got a few examples here. You have to recognize that the carbons overall are treated separately if it's a substituent versus the actual ring. So if it's just a ring, if there are no other substituents on it, then it's just named after that. So here I've got a 3-membered ring, it's going to be named after a 3-carbon group. The next example, we've got technically 2 carbon chains here. We have the ring chain, which is 4 carbons, and then we have the side chain, that straight chain, which is 2 carbons. And since 4 carbons are greater than 2, the 4-carbon chain, the ring, is actually the parent chain. In that third example, we again have 2 carbon chains. We have the ring, which is 3 carbons, and then we have this really long 8-carbon chain attached to it. And so in this case, because that 8-carbon chain is larger, that means that that's going to end up being the parent chain. The parent chain is that straight carbon chain of 8 carbons. So the way that cycloalkanes are named depends on whether the parent chain was the cyclic part or not. If the ring is the parent chain, then we simply attach a cyclo prefix to the parent name to indicate that that is a ring. So if you look at the first example, we have a 3-membered ring. A 3-carbon chain is called propane, so we now call it cyclopropane to indicate that those 3 carbons are in a ring. The next example, remember we had 2 carbon chains here, but we had decided that the 4-membered ring was the larger chain, so that means this is going to be a 4-carbon chain, butane, but that part is cyclic, so we call it cyclobutane. From there, we pretty much do what we did for alkanes. The next step is to number the parent chain. Now, with normal alkanes, we have to start our numbering from an end of the chain, but rings don't have ends. So in that case, if you have any substituents, you simply use those substituents to figure out where to start numbering the ring. The lowest number you can possibly give any substituent is 1. So if you only have one substituent, then that carbon that bears that group is going to be the 1 carbon. And then you simply number around in a ring. So here I've got my 4 carbons of my cyclobutane numbered starting with 1 at the location of that ethyl substituent. And that means this is just ethyl cyclobutane. Notice that I didn't put a 1 there for the ethyl, right? I didn't say 1 ethyl cyclobutane. And that's because the ethyl group is automatically on 1. It's not wrong to include the 1, it's just that most chemists don't do it. It's simply unnecessary because there is no ambiguity. There is no such thing as 2 ethyl cyclobutane. In the next example, we've got just a 5-membered ring. We've got 2 substituents in this case, right? And they're both smaller chains, a 1-carbon chain and a 2-carbon chain. So yes, the ring is the larger group. So this is going to be a disubstituted 5-membered ring or cyclopentane. And because we have 2 substituents, we could number either of those as 1. And there are no other substituents there to break that tie. So here we have to rely on that alphabet rule, where the group that is alphabetically first, in this case ethyl, gets the lower locant. So that way we have 1-ethyl, 3-methyl. And make sure you number the carbons of that ring in the direction that gets you to the next lowest substituent most quickly. In this case, I had to go counterclockwise to get to the methyl on 3. Had I gone clockwise from the ethyl carbon, that would have actually made the value higher. So how do we treat it if the ring portion is not the parent chain? Well, that means that the ring is actually a substituent. It's called a cycloalkyl substituent, very much like what we had with alkyl substituents. In fact, they're named kind of the same way. If you have a 3-carbon chain, it's propane, and then propane as a substituent becomes propyl. So here, if we have a 3-membered ring, which is cyclopropane, it now becomes a cyclopropyl substituent. And in all of the ways we name this the way we would normally, we number the parent chain, which in this case is an 8-carbon chain, so an octane. And we start the numbering from the left to get to the cyclopropyl substituent more quickly, putting it on 4. So we have 4-cyclopropyl octane.